the meantime, though, kind of fitting that this is our topic for today. Who is that on the screen? That is Raiden from Mortal Kombat, which movie opens tomorrow, I believe. I'm actually going to see it with some friends who used to play those games with me. It's pretty fun. Yeah, we're looking forward to it. Yeah, this was definitely my favorite character because he's the best. And he's the god of lightning and thunder. It's kind of hard to beat that. So, we did these types of PowerPoints earlier in the school year, kind of between units. And I stopped doing that because the smartboard died. And because I'm recording this, when I use this projector, it just does not show up very good on the camera. But I've kind of reserved myself to the fact that I'm not going to get a new one by the end of the school year. So we're going to be going through at least maybe one more of these next week, maybe on Monday. And then we've got one more to get ourselves completely caught up. So we'll just kind of see how things go and just roll with it. So electromagnetics is the sort of thing we are going to be taking a little bit of a look at today. You don't need to take notes, just sit back and enjoy the show. So, how many people have seen this before? Anybody ever done that? Yes. Yeah, a fair amount of people. So, there's something I kind of want to show you with this. Can I have a volunteer who's willing to get their hair messed up? Chip's got me, all right. Just going to get a balloon here. All right, Chip, if you would come on up, please. Take this balloon, get it nice and messed up in your hair there. Keep going a little bit longer. All right, that should do it. So, slowly lift that balloon off your hair, please. And, of course, what do you see? Yes, his hair is sticking up. And that is because of static electricity. And we're going to talk about that a little bit today. I can take that balloon from you, Chip. Give Chip a round of applause. Now, one of the neat things about static electricity is, let's just have maybe this group of people come on up here once. Take a look at the water. It's going straight down there, but if I put this balloon next to it, you see it move towards the balloon? Look at the bottom of the water there. Yeah. Very good. Let's have some other people come on up here. So as I bring the balloon closer, if you look at the bottom of the water, it's moving towards the balloon. There's not as much of a charge now, so it's not moving as much. But the water does move towards the static electricity of the balloon, which is kind of crazy. And, it's lost its charge. But what ends up happening when you stick this balloon near water is you see the water go kind of towards it. So first off, what's happening when this balloon is being messed up in Chip's hair there is the balloon is taking the negative charges from his hair and it's leaving just the positive ones. So when you have a difference in charge like that, we say something is charged. It has an electrical static charge. And because those charges are opposite, the opposites are going to attract, and Chip's hair goes upwards like that. And the same thing is true if you put that balloon near water. Because you've got a charged balloon here, and you've got water that has both positive and negative charges, this negatively charged balloon is going to pull the positive charges towards it. And that's why we see that bending occurring. It's kind of interesting. So yeah, that's what's happening. You've got negative charges on the balloon, positive and negative in the water. So the negative here pulls the positive there, and the water will go in that direction. How many folks have seen one of these things before? A couple people. It's called a Van de Graaff generator, and you can find these in like science museums and places like that.
Like Discovery World.
Yeah, like Discovery World, exactly. So what it does is it gives you a charge, and that charge has to leave your body, because if it doesn't leave your body, you are going to spontaneously combust, which means you'd start on fire. I don't have any proof that she didn't start on fire right after this, but you can see her hair is sticking up in every direction there. And the reason her hair is sticking up is because she's building up all of these charges, and they have to leave her body. And they leave in two ways, through her feet to the ground and through her hair. Now, if you've got all these, say, positive charges in your body and they're leaving through your hair, they're going to make your hair follicles repel each other because it's all the same charge, which is why the hair sticks up and seems to be moving apart from itself, because it's all the same positive charge. If you've got all the same charge, it's going to repel. And this is just a little bit of what's going on with that machine here. See if you can follow this reasoning. So you're going to begin down here. You've got positive and you've got negative charges down there, and it's pulling those charges from the ground. Now what ends up happening is inside the base of this generator, you see this little comb-looking thing right there? That's a special comb, and it's given a positive charge to draw all the negative charges off of this little belt here. Yes?
I'm not trying to be like rude, but what if you don't? Never mind.
No, that's
Yeah,
okay.
all of that, just to say
No,
never
because
mind.
I was gonna ask, and I was like, wait, it's kind of like dumb. I was gonna say, what if you like don't have hair, but like it doesn't matter, it'll still be right?
Yep, it'll still leave.
Okay, then.
Yep, yep. No problem. So yeah, we've got positive and negative charges coming from the ground, and it goes into the generator here on this little belt. And because this comb-looking thing here is positively charged, what it does is it pulls off all the negative charges from the belt, and that leaves only the positive ones. So those positive charges go up here. They're deposited on this little comb thing, and they land on that big metal dome for you to touch, and those charges then go to your body and out through your hair. So that's how that machine works. I actually have one in the back, and I get it running, but it doesn't work anymore. We actually fixed it in AP Physics 2 years ago, but then the belt broke and started on fire, so we don't use it anymore. So here's a lightning bolt. Might be kind of interesting to know exactly how lightning works. We talked a little bit about it a while ago. The main thing you might remember from the speed of sound chapter was the fact that it takes about 5 seconds for lightning between the time you see it and the time you hear it. If it takes about 5 seconds, then it's a mile away from you. But if you see the lightning bolt, every second after that, between the time you see it and the time you hear it, that corresponds to about 3 football fields. So it kind of gives you an idea of how far away these lightning bolts are. Every second you count between the time you see it and the time you hear it is 3 football fields. If you get up to 5 seconds, that's a full mile. So the way lightning works is you've got clouds, and generally your storm clouds are going to have negative charges on the bottom, and the ground has positive charges and negative charges. But of course, if you've got negative charges up here, that's going to attract the positive charges from the ground. So the ground has both positive and negative, but because this is negative, it's attracting the positive charges upwards. And basically, what the lightning is trying to do is it's trying to equalize these charges. The negative charges are going down, positive are going up. If and when they connect, you get a lightning bolt. This kind of brings up something in terms of safety. If you're ever outside before a lightning storm, or if one's happening and it's not raining, and you kind of see your hair or feel your hair starting to go up like this, that is bad news, and you want to bend down like this as close to the ground as you can get, Because what that is it's the positive charges from the ground ascending upwards, trying to meet up with the negative charges from the cloud. And if that happens and it goes through your body, that's not good news. So this is kind of I've only seen that happen once. The person didn't get hit with lightning. They responded appropriately. But it's scary stuff. I mean, there's a chance it could, but the chance is much less if you go down and go like that, yeah. Because you really don't want to be the first thing that connects with this negative charge here. Generally, it's higher things like trees. Just because it's coming up through your body doesn't mean it's also not coming up through something else. Yes. Yep. You want that charge to connect somewhere else. Now, this is kind of a... Sorry, was there another question?
Yeah.
Yeah.
Sorry. How much time do you have to, like, respond?
It depends. It all depends. You know, if it's completely flat and there's no other large things around, you might have 30 seconds. Otherwise, yeah, if you're in the midst of a forest, you're probably not going to get hit no matter what, because it's climbing up other trees that are much closer than you. But yeah, main thing, if that's happening, you want to get down to the ground, or better yet, get inside. Now, this is a simplistic diagram of what's actually happening with these thunderstorms. The real thing looks more like this, so it's more complicated. And you can actually have lightning go between clouds, too, because you've got different charges. So, anyway, just thought that was kind of interesting. So, conductors. In terms of electrical charge, some things allow that electrical charge to flow better than others. Conductors allow it to flow really, really good. And these are the best conductors in the world. We've got copper, gold, and silver. Anyone want to guess which of these three is best at allowing charge to flow? Copper. Good guess, but you're wrong. Anybody want to take another guess? Gold. Good guess, but you're wrong. Sorry. Silver. It turns out silver is the best thing that conducts electricity. And yet, in every house, when we look at the wiring, we find copper wiring. Why do you suppose that is? Yeah, it's way cheaper than silver. I don't know if there are any super rich people that wanted, the best conductivity, so they got silver wiring. But yeah, generally you see copper in houses because it is a really good conductor. It's not that much slower than silver, and it's definitely super cheap. Insulators are a different story. These things prevent charge from flowing through them. Two of the best kinds of insulators would be glass and wood. So yeah. In terms of electrical charge, you may have seen one of these things before, and we're going to test this out near the end of class for anybody that's interested, where we're going to join hands in a big circle of friendship. But before we get to that, I'm going to plow through this as quick as I can, and we'll get to that, because that's really the fun part. So there's this thing, and like I said before when I'm done this is something that we could do for an entire couple chapters, 2-3 weeks if we really wanted to. But it's one of those things where you can kind of summarize it into some main points pretty quickly. And that's what I'm trying to do here. Like we could spend a couple days on electric induction, when basically what it is simply isolating a charge. And the method that you could use to do that is, here's a little dome. It has no charge. Then you give it both positive and negative charges there by simply attaching it to the ground. And then what you can do is if you bring some charged rod next to it and you attract the positive charges to the left, you could then ground the right side, and those negative charges will then be attracted to the positive ones in the ground. And you're left just with positive charges then, and you have yourself a charged metal ball. So that's kind of a slow way to do a Van de Graaff generator, and this would be very weak compared with it, but it's the sort of thing that you can do. So when we talk about electric charges, this is how we would diagram this if I was giving it out as homework. Positive charges would have field lines going away from the positive charge. Negative charges, you would have them going in. Again, we have to choose directions with this, just like we choose directions with momentum and force and velocity. And those are the directions we would pick. On your formula sheet, you would find this equation here. It's something that can show us how strong an electric field is. An electric field is nothing more than a static field. If you rub this on your hair like Chip did, and then you bring it close to your hand, you'll be able to actually feel the static. You can kind of hear it crackling a little bit. And this is simply a measurement of how strong that crackly field is. As you can guess, as this would get more and more complicated, these electrical field lines would get more and more complicated. We speak of the fields as going from positive to negative. And if you've got two positive charges, they would repel like that. And, you know, there's really no need to go much deeper than that. Another picture here, flowing from positively charged to negatively charged. If you've got yourself a positively charged and a negatively charged balloon, there's really no way to tell the difference between the two. But yeah, it's just a matter of drawing them in. And you could do this three-dimensionally too if you really wanted to on a computer program. This would be two opposite charges attracting each other. And this would be two like charges repelling each other in a three-dimensional environment. And there's some other equations you could deal with here too. In terms of electrical force, you could measure how much force is a part of that electrical field, and you could actually calculate the amount of potential energy that electrical field has. I believe these two equations are also on your formula sheet if you would take another physics class in college. So they are there for you, even though we're not really spending too much time here. And you can see these fields can get complicated based on the different charges that you have. It's just kind of interesting to look at. I'm not going to go too in-depth here. And more charges. And if you really take this to its ultimate conclusion on, in terms of complexity, ultimately what you could do is you could put different charges in a three-dimensional world, and you could place a charge in any location and then at least be able to estimate the direction that charge would go if you release it and let it go. So this is getting really sophisticated and complicated. We don't need to talk too much about that, but this is where you'd eventually go with this stuff if you really wanted to get into electric fields. And that's more university level right there. There are easy ways to block electric fields. All you really got to do is put something in front of it. This is why if you're driving down the road and you get hit with a lightning bolt, you'll actually be just fine, because that charge stays on the surface of your car. It does not penetrate to the inside. So you'll be fine as long as you're inside your car. If you happen to... Yeah, the car will generally be okay, because what happens is the charge is not looking to destroy your car. It's just trying to equalize. So essentially it's trying to get to the ground. So it just takes a path from your car, usually then through one of the tires, to the ground. And you might see a couple side effects of that, some burn marks, but generally cars are okay if they get hit. It is a very rare occurrence. You might have, especially now, you probably have some shorting going on in the computers in your car, but overall the body of the car should survive just fine. And you'll be okay too, so long as you're not sunbathing on the roof or something. So yeah, you can ground them, meaning equalize them, or you can encase them in something. Now, everybody has smartphones, and when you activate your smartphone and you're playing with it with your finger, what do you suppose it's responding to when you do that? Like if I go like this, what's causing it to do that? What's going on here? Anybody want to take a guess? It's kind of an interesting question, isn't it? Charges? You probably, you're on the right track here. So a lot of times people think that, it's responding just to the pressure that you put on it. But you could use, you could use something other than your finger and press real hard and nothing's going to happen. It doesn't respond. So it's not pressure that responds to. What it actually is responding to is the electrical field inside your body. Every single person has an electrical field that they are emitting, and that's why it's responding to your finger and nothing else. This is why when you see people with these fancy gloves on, that their phones still work. Because on the thumb and on the forefinger, they kind of have these metal-looking things, and that's because they're conductors on the ends of your finger. And because it's conducting, it allows the current and the electrical field to run from your finger to the screen of the phone. If you try and do this with regular gloves, it's not going to work. You got to have those special gloves on, or you got to have a special stylus which would have some sort of electrical charge at the bottom. So yeah, everybody emits an electrical field, and I can prove that to you. The batteries are actually running kind of low on this thing, so it normally would emit a sound. I'll just kind of let it sit like this so you can see the needle there. And all I'm going to do is just kind of wait for the needle to settle a little bit. And this is an electrical field detector. So if humans emit electrical fields, then it ought to react if somebody would walk across it. So let's see if it reacts. You see the needle go nuts when I walk by? It's because my body has an electrical field, which is ultimately produced from your heart and the electrical impulses that your heart sends out. So, again, I'll just walk past it, and the needle deflects rather madly because I have an electrical field in my body, and it's causing that device to activate in that way. It's more, you can actually, the neat thing is you could actually use this as like a burglary detector, or you could just to see if anybody has walked through the room, because you can set the sensitivity of the sound. So if someone walks by, it'll instantly make a little beeping noise. It's kind of interesting. So let's get through some more things here. Magnets. How many people know what a magnet is? Oh, good. They've got north and south poles, and they attract metal objects. These are your standard magnetic materials here, iron, cobalt, and nickel. And in the same way that you can isolate a charge and give something an electrical charge, you can also give something a magnetic charge. So these are some paper clips there. And you can see there's some at the end here that are kind of just barely hanging on. And the reason I can make a chain this long is not because the magnetic field from the magnet is actually acting that far. What's going on is this magnet is turning each of these paper clips into temporary magnets. So these all have their own magnetic fields right now, temporarily. And that's why they're able to act as their own mini magnets. I think we found the breaking point right there. So yeah, and as soon as I would take the magnet away, they stop becoming little mini magnets then. And that's called magnetic induction. You can actually make mini magnets out of things as long as they're in a magnetic field. And unlike electrical fields, it's very difficult to block a magnetic field. So yeah, it acts right through your skin and hand and anything. There are only a very limited number of ways that you can block a magnetic field. You can see it's even acting at a pretty big distance there. And that's called magnetic induction. Something else that's interesting about magnets is if you break them in half, you do not get an isolated north and south pole. It breaks up into north and south poles once you do that. You'll always have both sides of a magnet there. You'll never be able to isolate it. And magnetic field lines are kind of the same thing as electrical field lines with a few small differences. And you can just kind of see these magnetic field lines. They look very similar to the electrical ones. Equation for magnetic fields is that. That's also on your formula sheet. North and south poles attract. North and north repel. I'm sure this is all review. We're going to power through these slides here. And you can then draw these magnetic field lines in the same way that you could draw the electric field line. In terms of magnets, we interpret the north pole as shooting the magnetic field out and the south pole as receiving it. So if you're attracting two magnets like this, you would draw them with arrows going from north to south. And you get the idea. More fancy equations. You can find magnetic force. You can find magnetic potential energy. Ta-da! More stuff. Earth has a magnetic field. This is kind of where it gets a little interesting here and sort of down to the real world. The Earth, if it did not have a magnetic field, we would all be dead in very quick order, because the sun is a big ball of radioactive gas, basically. It's called plasma, and it shoots out this plasma in something called the solar wind, which sounds like a warm breeze, but it's not. It's basically radiation that would kill you if you didn't have protection. Thankfully, we do have protection, and it's our magnetic field. Our magnetic field interacts with these charged particles, and it deflects them outward. Now, as you can probably guess, in the same way that a north and a south pole on a magnet separate, our magnetic field on Earth separates too. So there's a little area here where some of these charged particles can make their way through to our atmosphere. Any guesses on what happens when that occurs? Northern lights, exactly. When these charged particles, a few of them make it past our magnetic field and into our atmosphere, we see the northern lights, and that's what produced those. Our atmosphere protects us from any harmful radiation that those particles would bring in. So if we didn't have an atmosphere or we didn't have a magnetic field, we'd basically be screwed. But we have both, and so we're protected. That's one of the easy ways to see how well designed this Earth is. And our magnetic field is so fine-tuned. And our sun is actually, despite the fact that it's sending out radiation everywhere, it's actually very well behaved compared with most of the stars that we observe in space. We're literally in the only type of solar system that we could be in and actually live and thrive and not die based on the radiation from our nearby star. So the sun does have a magnetic field as well. And it looks kind of crazy compared with the Earth. And you can see these sunspots here. These sunspots are the result of the sun's magnetic field. The reason that they're there is because... How much time do you want to spend on this? You guys know what convection is, right? Warm air rises, cold air descends. Same thing is true on the sun. So in the middle, it's got a whole bunch of nuclear reactions that are going off, and it sends out super hot gas and ionized particles outwards. As those particles get further and further out, they cool off. And once they get near the sun's surface, they'll descend. Well, if the sun has a magnetic field that's going up and down like this, that interferes with that convection cycle. And it does not allow the really hot material, which has gotten to the top, to descend once it cools. So all the cool material is blocked from descending here and heating up again, and that's what causes these patches. And those patches, when you see them, are actually very cold regions on the sun compared with the surrounding area because of the interruption of that convection cycle. And sunspots go through cycles like this. We're down here. There aren't too many sunspots right now. And then they'll pick up again a little bit later. About every 11 years, the sun goes through this cycle. Its magnetic field actually flips every 11 years. So it's kind of crazy stuff that goes on the sun. If you're interested in this or other astronomy-related things, take astronomy because we go into more depth in that class. So this is called a prominence. It's something that occurs as a result of the sun's magnetic field, much larger than the Earth, but it does not reach the Earth. What does reach the Earth are solar flares. And these are the things that we have to kind of keep an eye on. In 1859, we had the largest solar flare ever recorded hit Earth. And what it did is it messed up all the electronics on Earth. All of the telegraph wires basically went up in sparks. And the aurora were so amazing from this solar flare, because so much of it got through our magnetic field, that actually people at the equator could actually see the northern lights, which is unheard of. Folks in the Rocky Mountains who were miners actually got up at around midnight because they thought it was so bright, they thought the sun was coming up and they were getting ready for work. So it was crazy how big this was. And it's interesting to think about what could happen these days if this happened, now that we're so much more reliant on electricity and electrical devices. So, you can block magnetic fields. You need some really strong iron to do that. You could also destroy magnetic fields by heating them up enough or by smashing them with a hammer. Hammer time. Okay. There is a connection between magnetic fields and electric fields. Basically, a quick summary of it would be if you've got a changing electric field, that's going to produce a magnetic field. And a changing magnetic field will produce an electric field. So they're connected like that. I'm just going through this kind of quick. I want to make sure we have time to do the activity at the end of class here. Now we can actually determine what direction current is going to go based on the magnetic field and the direction it's going. It's through something known as the right-hand rule. AP Physics learns about this. Basically, you take your right hand and you take your fingers, whatever direction that magnetic field is going. In this case, it's going to be going counterclockwise. You take your fingers, curl them in that direction, and your thumb points in the direction of the current. You can see that here too. It's going counterclockwise, curl your fingers, thumb points up. That's the direction of the electrical current there. And there's a couple different pictures that show this in different ways. And you can actually increase the power of your magnetic field from this current if you put iron through a coil like this where electricity and an electric field is running through it. So yeah, if you've got a current and you want to increase the magnetic field produced by that current, you can throw some iron in there and that's going to have that effect. You can also produce an electrical field simply by putting a magnetic field through an iron rod like that. So again, these things are very connected. Electrical fields and magnetic fields are basically holding hands. They're friends, and where there is one, there's usually another without too much without any time where that doesn't happen. That usually occurs. You can actually make electricity with this. If you have a flashlight and you shake it a lot, it moves this magnet back and forth, and through induction it gathers a charge, and it acts like a battery, and you can actually use a flashlight in that way without an actual battery on the inside. You're just charging it up by shaking it and giving it that electric field. And a couple cool three-dimensional magnetic field images here to wrap this all up. And things can get complicated based on, you know, if you've got something that looks like this and you want to figure out the direction of the magnetic field, you got to go and do the right-hand rule, and it changes based on where you are as this goes around like that. So things can get complicated. There's a neat little animation there. Electromagnetic fields. This is just when you have both fields present at the same time. There's an example of one. I have a device that we don't have time to test right now, but it's something that you can turn the electric and magnetic field on and off just with the battery, and I'll show you how strong that can be in a little bit, maybe next time. So yeah, they're connected. You can kind of think of it like having two axes here. Maybe one axis would be a magnetic field, another would be an electric field. If you change things on one axis, it will affect the other. So they are connected like that. And that's a nice, cute little background there that apparently incorporates electromagnetic fields. Okay, so to kind of close this up then, I want to show you a couple cool things that the folks at home unfortunately will not be able to see. So, see you later.